Okay, there we are. All right, so today's lecture. So there's two things in here. Okay, so I think you remember a while ago we were talking about elliptic curves where we considered curves y squared equals x cubed plus ax plus b, where a and b are integers. And we made up several of them at random by you shouting out integers a and b, and then I just typed them in, and we saw what happened. And in each case we computed generators for the group of points on the elliptic curve. And for some bizarre reason, every time we tried this randomly, we got a curve where there was one generator when we were doing it randomly. So I asked one of my PhD students, Simon Spicer, to systematically look at curves of this form. And there's a notion of the height of such a curve. It's a measure of the complexity. And for very natural reasons, which I won't explain at all, the height of y squared equals x cubed plus ax plus b is the maximum of the absolute value of a cubed and b squared. So, in other words, if a and b are really, really small, then this has small height. If a and b are big, if either one of a or b is at all big, then it has bigger height. And so a question you can ask is, what's the simplest in terms of smallest height curve where you don't need any generators, where you need one generator, where you need two generators, etc., in order to give independently all the points? Yes? It's literally, by definition, simply the maximum of the absolute value of a cubed and b squared. That's it. It measures the size of the curve. It's how tall it is. I mean, it literally, like height, like my height is, something that measures how big I am. And this similarly is measuring how big it is. Like if you were to print out the curve, it takes up a certain amount of space. And that space is more or less the height. It's kind of like the logarithm of a number, but I mean, this is just a very simple measure. So if you made up a random curve and a and b each had, like one digit, then this height would be pretty small. Okay? It makes it so you can order elliptic curves in some systematic way. There's going to be finitely many curves of each height. So that's a good statement to practice with height. Prove there are finitely many curves of each height. So, or even better, of bounded height. So if I say, consider elliptic curves where the maximum of these two numbers is at most 100. Remember, a and b are integers, which isn't explicitly said here. Why are there only finitely many such curves? This should be really easy, but we'll see. Maybe it isn't. Any thoughts?
You run out of numbers.
Yeah, you run out of numbers. Right. Imagine that the maximum of the absolute value of a cubed and b squared is less than or equal to 100. Then b can't possibly be bigger than 10, because if b were bigger than 10, b squared would be bigger than 100. And similarly, a can't be bigger than cube root of 100. And there aren't very many integers whose absolute value are less than those two things. Okay? So given any cutoff, there's only finitely many curves with height up to that cutoff. And so what he did was he just made a list of curves with really ordered by this number, the height. And then he found the first one with rank 0, rank 1, rank 2, rank 3, and rank... He found small ones of rank 4 and 5, so the minimum number of generators needed is 4 and 5. But in those cases, he doesn't know that they're the smallest height ones, because it's actually really hard to compute the number of independent generators. Anyways, here's what they look like. It's kind of ugly, isn't it? That's hard to look at. I'll put some space in so it's easier. Here, and I'll zoom out temporarily. So, sorry for the brace. So it's y squared equals x cubed minus x. That one doesn't need any generators. I mean, there are a couple of torsion points. That's it. And then another simple one is y squared equals x cubed minus x plus 1. There you have rank 1. Y squared equals x cubed minus x plus 4. There you need two independent points. And it's still a very simple curve. And then here's another one, y squared equals x cubed minus x plus 25. And there you need 3 independent points. And you can see them minus 3, 1, minus 1, 5, and 0, 5. And then here's one that needs 4 independent points to generate all of the points. Y squared equals x cubed minus 19x plus 151. We don't actually know for sure that that's the simplest curve that requires 4 independent points. And here's one that requires 5. Okay, so I just wanted to mention that. Moving on to the elliptic curve digital signature algorithm. So that's what we're going to spend the next 2 or 3 lectures on. This is a protocol, well, it's an algorithm. I mean, I have to call it algorithm because its official name is ECDSA, with an interesting history and present. It's a very popular application of elliptic curves in the real world, which is in the news off and on and so on. So just to give a little sense of how this thing pops up. So here's an article that's in, I guess it was a couple of years ago in Ars Technica, PlayStation 3 hacked through poor cryptography implementation. So that's why. So PlayStation 3, I have one in my living room. Maybe, does anybody here have a PlayStation 3? So some of us have PlayStation 3s. And apparently some hackers hacked it, which made it easy to pirate games or something. I don't know what they did with hacking it, but the interesting thing is that they were able to somehow sign off and escalate. They're able to do things that you're not supposed to be able to do. This was supposed to be very hard to do, but basically the people in probably Japan who implemented the cryptography in PlayStation 3 messed up. They made a big mistake in implementing ECDSA. And so I'm just telling you that because when I show you exactly how ECDSA works, I'm going to show you step by step what it is. It's something similar to the RSA for digital signatures. It's just more complicated. You'll see it in a minute. I'll show you the step that they messed up. And you'll be like, how could they possibly have been so stupid to do that incorrectly? But they were. And I mean, they did it. Their manager signed off on it. It got shipped in a deployed product, etc. And it gives a good example of how easy it is to mess up when you have some complicated algorithm. Okay, so here's another thing. Here's something in Forbes, I guess today, actually a few hours ago. So Bitcoin hit by a massive attack. So if you read this, you'll find that the attack involves this signature algorithm, but so let me read the exact part. Well, basically this algorithm that I'm going to describe, elliptic curve digital signature algorithm, is used to sign off on each Bitcoin transaction, except there's a little bit of extra information, a transaction ID, which is like a hash of the whole thing after you do the signing, that goes along with the transaction. And it turns out that given the way things are currently implemented in a lot of situations, a little trick allows you to possibly steal large amounts of Bitcoin, which is very motivating to certain people and has brought Bitcoin to its knees during the last few days. Here's the price of Bitcoin recently, and here's the price of Bitcoin right now. So it's like half what it was worth a month ago or something, or even a couple of weeks ago. So there's like a war going on online involving Bitcoin. Yes?
Is that an interactive file? Like, could you click on the one day?
Yes.
And see?
This I can't. This is an image of it, but it's
Okay.
easy to find links to this sort of thing. I unfortunately didn't make it a link.
Oh.
Sorry. But yeah.
I'm just curious. It seems like it's just plummeting in the list.
It is plummeting.
Because that's that should be 365 days.
Because basically what happens is each time a transaction is made, the elliptic curve digital signature algorithm is used to sign that transaction. And then this extra hash is made, which is the transaction ID. And what happens is people try to make, say, a withdrawal. And what happens is somebody makes a withdrawal, and then very quickly they make another transaction, but they change the hash by putting a 0 in front of it, which a lot of software will recognize as being the same hash. But the Bitcoin exchanges like Mt. Gox, don't recognize it as being the same hash. And so somehow that one goes through a little bit more quickly, and then the exchange thinks that the whole thing didn't go through because they're basing it on the first hash that they used, whereas the one that went through had the second hash. And so, so the Bitcoin exchange thinks that the withdrawal failed, but in fact it succeeded. And so then the person tries to withdraw again, and they just keep getting to withdraw their same money over and over again, except every time they're getting new money. So that's a very, very rough sketch of what's going on. So basically, most of the exchanges seem to have shut down because, temporarily they claim, because of these repeated attacks. But what I'm going to tell you about isn't so much the attacks right now, but what the elliptic curve digital signature algorithm actually is. Okay? This is not an easy algorithm to understand. It's significantly, it's like a one step more complicated than RSA or Diffie-Hellman. I apologize for that. There's nothing I can do about it. It's simply more complicated. It's just enough more complicated that, I mean, just think about it. Sony hires a bunch of people. They have several levels of management, whatever. They still shipped a completely messed up implementation of this. So don't think that this is a trivial thing that I can explain in 1 minute that you'll perfectly understand first try. It isn't that complicated, but it is still not completely trivial. But I want to spend some time motivating what it is first. So first, it's a protocol that really solves the same problem that RSA solves, namely, you can digitally sign a message. And I'll recall in a moment, just so you remember exactly how that works with RSA. And you might ask, why bother doing something new involving elliptic curves that's more complicated when you already have RSA? And I guess there are a couple of answers to that. One is the sales pitch, namely that that you can end up with something that seems to be just as secure as RSA, but everything involved is way faster, the keys are way smaller, etc. And that matters a lot in practice. The speed of carrying out your encryption is really, really important because a lot of devices that do encryption, I mean, our phones and stuff are getting better and better, but they don't really get, the processor speed doesn't necessarily get faster for a single task. So it's kind of annoying if things are really slow. Okay, so first, there's that. That's what you see a DSA does. It solves exactly the same problem RSA is supposed to solve. You can take a message, you have some public key that you publish, you take a message, you sign that message, and you get a signature of that message, and other people can verify with high probability that you had to have been the person that signed the message, not somebody else. The message, in the case of Bitcoin, is something like, I transfer this money from here to there. And you want to be able to sign that and guarantee that it really is something that you intend to do rather than somebody else. So being able to digitally sign documents, as you might imagine, has a lot of value. Another way in which it's used is, let's say you want to be the only person that's allowed to create software that can run on the PlayStation 3. So what you do is you digitally sign the software and you make it so the PlayStation 3 will only run software that was properly signed. So like the secret information needed to sign is different than the information needed to verify that the signature is correct. So correctly implemented, the information on the PlayStation itself isn't enough to break the encryption scheme, if done correctly, which it wasn't. Okay, so ECDSA, this algorithm, was introduced by a guy named Scott Vanstone over 20 years ago. He founded a company called Certicom, and amazingly, they actually rent elliptic curves to the NSA. I mean, that sounds crazy, but renting elliptic curves sounds crazy. To the NSA sounds even crazier. And the most amazing thing is they've made over $25 million in revenue by doing so. So there's like so many levels of crazy there, but just a on-record fact. You can also read about, there's a lot of stuff, like this is an article from a few days ago about how the random number generator that had a backdoor that the NSA designed, Certicom employees patented that very random number generator and started pushing it. And they were also apparently receiving a $10 million contract from the NSA at the time. By the way, I was talking to the guy who discovered the backdoor in that random number generator this morning, and he said he'd come in and give the class on March 5th. So he'll come in and give a talk about how he found this backdoor in the random number generator next month. So I'll remind you again so you make sure to come to class that day. Okay, so he said he can't give the class this week or this month because he's going to be on some panel with like some of these guys about exactly this factor somewhere else. Okay, so now more motivation for ECDSA. So here's how I'm going to motivate you a little more to appreciate ECDSA. Since I'm going to show you, I'm going to show you ECDSA in a moment, and it's going to look complicated, and I just want to prepare you for it. So first, very quickly, I just want to remind you, so it's in your head, how Diffie-Hellman and RSA work for digital signatures. Except Diffie-Hellman doesn't do digital signatures, but RSA for digital signatures. So all right, that is freaking annoying. Okay, so here's how Diffie-Hellman works. You choose number G mod P and a prime number P, and one person chooses a random number n and sends G to the n. Another person chooses a random number m and sends G to the m. Then the secret that they both know is G to the nm. So hopefully you could just remember that in your sleep at this point. And then RSA for digital signatures, it's right here. And here's what you do. You create a public key, which is obtained by taking a product of two large prime numbers, n equals p times q, and a random number e, which is co-prime to phi of n. Because you constructed n as p times q, you can easily compute phi of n, and hence ensure that e is co-prime to phi of n. But you can also compute the multiplicative inverse d of e modulo phi of n. So in order to now use this data to digitally sign, here's what you do. You take your message, you hash it in any way at all. So you take a big message and construct from it a little number that is constructed in such a way that it's very difficult for somebody to come up with a completely different message that hashes to the same number. That's the idea of these cryptographic hash functions, which I haven't said much about. But one of the most popular ones is called SHA-512. That's one of the best ones. They're also used in passwords. So like when you set your password on cloud.sagemath, it takes it and applies the SHA-512 hash function, iterated 1,000 times actually, to get some random looking thing, and that's what it stores in the database. And when you enter your password each time, it takes the password, hashes it, and then checks it against the hashed version in the database. The reason being that if somebody steals the database, it will make it very, very difficult for them to figure out what your password was in the first place. Basically, they have to guess your original password, run a slow function against it to try to check that it's what's stored in the database, and that can take a long time. So it gets used there, but these hash functions get used quite a lot, so it's a whole big deal. But it has nothing to do with number theory, so I'm not going to talk about it much. Okay, you verify the signature so you sign the document by taking the hash and raising it to the power of D, your private key, and that's the signature. And then you verify the signature by raising the signature to the power of E, which is your public key. So it's amazingly, beautifully symmetric, incredibly simple to describe, and that's it. So that's how digital signing works with RSA. Again, ECDSA is far less straightforward than this, unfortunately. Sorry. Okay, so now let me zoom in here a little. Okay, let's suppose we wanted to. Okay, so first, RSA just doesn't make any sense if you try to do it directly on an elliptic curve. You can try to make sense of an elliptic curve mod p times q. You can do various things, but at the end of the day, you find out that it just doesn't work. You don't get very good security, and everything kind of breaks. So if we wanted to somehow use elliptic curves to do digital signatures, you can't just sort of very, very easily convert the RSA method to elliptic curves. I don't know any way to do that. So you might think, well, maybe somehow we can come up with a digital signature algorithm using Diffie-Hellman, or something very much like Diffie-Hellman, because Diffie-Hellman directly translates to something you can use on an elliptic curve. With Diffie-Hellman, remember it's just going up again. With Diffie-Hellman, all you do is you compute g to the n, g to the m, and then g to the nm. There's an easy analog of this on an elliptic curve. You compute n times a point, m times the point, and then the secret is n times m times the point. So it's really, really easy to generalize Diffie-Hellman to an elliptic curve. So if we could come up with something that's very similar to Diffie-Hellman and does digital signatures, then that would be easy to generalize to an elliptic curve. So here's a little attempt at that. That fails completely. But it fails in an interesting way. So fix your G and P just like with Diffie-Hellman. Basically what we'll do is kind of like half of Diffie-Hellman. So you fix your G or P and you generate some secret n and publish G to the power of n. Your private key is n and your public key is GP and G to the n. And by the way, this isn't a completely ridiculous thing to do. ECDSA will be similar to this. It's just it uses some extra structure that makes it more complicated. This doesn't work, but it's interesting. So all you do is, here's how you digitally sign. Here's your public key. It's like you've done half of Diffie-Hellman. And let's say you have your message, you hash it to some number t, and here's how I'll sign. My signature, what I'll do is I'll choose a random number m, and I'll publish g to the power of m, and my hash times g to the mn. That's my signature, the pair g to the m and t times g to the mn. This is something I can compute because I know g, I know g to the n, I know n, I know everything. And so I can compute this. And I'm not really giving away, hopefully, too much information. I'm not giving away what n is in computing this. Like you might think, oh, I'll just divide g to the mn by g to the m, but that gives you g to the mn minus m. It doesn't give you g to the n or anything like that. I'm just saying that computing this and publishing it as the signature, I think, doesn't give anything away. Okay, here's how you try to verify the signature. The signature is something that I can compute because I know the value n. I randomly generated it. I publish it, and now let's see, how can you verify that I was the one that did it? So what information do we have at this point? You have g to the n, g to the m, t, g to the mn, etc. At least you have these big-looking numbers that claim to be g to the m and t times g to the mn, and you want to verify that they really are. So basically you end up with the problem, given g, p, g to the n, g to the m, and g to the nm, confirm that g to the mn really is g to the nm. I mean, it seems easy enough, and of course it's possible in theory if you were willing to wait 10 to the 64 lifetimes of the universe. And you might think, oh, maybe there's some clever trick, but if you think about it for a while, it starts to seem really difficult. Like, what can you possibly do? Given these numbers, how can you verify, say, that the last one really is g to the nm and not just some other random number? So these look kind of like, letters. They look like algebra. But imagine, since you're so used to working with these for the homework problems, these are each just numbers mod p. They're just like 100-digit numbers, right? Every single one of these is just a 100-digit number. And how can you, like the person, their signature is basically, to believe the signature, you have to believe that a certain number really is g to the nm. And it's just like, how do you verify that? I can't think of any way. If you have g to the n, you have g to the m, you can multiply them together, that gives you g to the n plus m. So that doesn't tell you anything. And there's just nothing algebraically that you can do with these that will allow you to confirm that g to the mn really is g to the nm. Yes?
A question about the version 1 part.
Yes.
Usually if I take a log of base gn
Yes. Then you're good. If you could take, that's the discrete log problem though. Everything you're doing here is working modulo p, and you can't efficiently take logarithms when you're working modulo p, as far as we know. That's an assumed to be very difficult problem. So when I write this, it would be ludicrous for you to not always be reducing modulo p, so it's implicit. Okay, I don't mean to do this directly with integers that have bazillions of digits. Everywhere here, you're always reducing modulo p. Okay, so you're just asking about the discrete log problem, I think. So it appears to be a very difficult problem given g and g to the m to figure out what m is. I mean, you could certainly write log base g of g to the m, but when you're working modulo p, there's no efficient way of computing that. If you think about it, the way on a computer or with a calculator it computes logarithms is that usually they'll have like an infinite series, and it adds up terms of that series and gets better and better approximations. That just doesn't work or make any sense at all when you work modulo p, because it's just a different world. Okay, so in fact, there's something called the decision Diffie-Hellman problem, and if you look at Wikipedia, you can look at discussions about this. But basically, it's just a hard problem. Given all these things, it's hard to know if this really is g to the nm. It's kind of kind of weird. It's like if you had some magic box that figured out what the secret key is, you couldn't actually verify that it really was the secret key here. So that's the kind of situation we're in. So we need a better idea. And here's what we can do. If we switch from using Diffie-Hellman mod p to working with an elliptic curve mod p, then we get something very similar to this, but there's something a little extra going on, because with an elliptic curve you have both the additive group of the elliptic curve, and you have, if you set things up right, you also have a scalar multiplication. So like you can take elements of the elliptic curve and multiply them by things. So there's just a bit of extra structure that combines how the points are represented with, well, I'll just show you. But there's a little bit of extra structure that is just enough to set up a signature scheme. So now I'm going to show you, no holds barred, nothing skipped, exactly as it is, the elliptic curve digital signature algorithm protocol. So these are the steps. They seem to be hidden by the HTML, but it's not too bad, but it is a little weird. And there are choices to be made, but here's what you do. Step one is almost the same as what we did above. Basically, in step one, we're going to set up half of the Diffie-Hellman key exchange. Except there's one funny, arbitrary, very unpleasant to a mathematician thing that you do, which you do. So here it is. So we choose a prime number q, and an elliptic curve mod q. So you just do this however you want. And of course, this is exactly what Certicom does cleverly and then sells for $25 million. They rent a curve for which they believe it's been chosen very well. So you choose your prime number q, you choose some elliptic curve mod q, you choose a point on that elliptic curve. So it's just like if we were setting up Diffie-Hellman. And we're going to choose the point to have prime order p. So remember at the end last time we learned that you can compute the order of the group of points on an elliptic curve mod q efficiently, and hence computing the order of a point on the curve, that's not much more difficult. Once you know the order of the group, you can easily get the order of any point in the group. And then here's the really weird thing you do, which is kind of it's an extra kind of weird arbitrary thing, but it's not, I mean, there's some standard ways to do this. You define a set theoretic map. So this is not it has no algebraic structure at all. Just define some map that maps fq to fp star. So by fp star, I mean the non-zero numbers modulo p, and by fq, I mean the numbers modulo q. And one way to do this, you can represent the numbers modulo q as integers between 0 and q minus 1. If you took such a number, you could just reduce it modulo p, and that would give you a number between 0 and p minus 1. And if you happen to get 0, just make it 1 arbitrarily. Okay, so that's, you just choose some arbitrary way that spreads the numbers out mod q modulo p. Okay, so there's a million different ways to do this. You just choose one. And then you just fix it once and for all. Okay? It feels unnatural, but it is useful to do this. And then you choose a random secret number, d, and you compute q equals d times g. Again, this is very similar to what we did above. It didn't work. We're doing the first half of setting up. It's like we're doing our part of Diffie-Hellman, plus we're defining some map that will allow us to get numbers mod p out of our points on the curve. Any questions so far? Yes?
Is it p needs to be like surjective or?
Nope. You might as well make it surjective, but I'm to set this up, you don't need any properties at all. It could send everything to 1. Your crypto system would be very insecure if you do that. And don't worry, Sony was not that stupid in their implementation. But it doesn't have to be surjective. No. Any other questions? Okay, so we're just introducing this, or Scott Vanstone introduced this because it turns out to work. And it's pretty amazing, but it does give you something new. Okay, so you choose a random secret, and you compute Q, which is D times G. Again, this is exactly like you're doing your half of Diffie-Hellman, and you're choosing some funny random map. And now your public key is the elliptic curve, the point on it of prime order. Might as well record the order of the point so other people don't have to recompute it. And Q, which is this random multiple of G. And note, of course, that you're keeping the thing that you multiply G by secret. That's your private key. You're going to use that somehow in signing messages. Okay? So hopefully, note there shouldn't be anything really scary so far, except this is not scary, it's just annoying. Okay, so next, the next step, you have a message you want to sign, so you compute a hash of that message. I won't say more about that. You could just imagine you're signing an element of FP star. Just think of it that way. Okay, now here's the third step. You make a random point that's a multiple of G. Now you're kind of doing the other half of Diffie-Hellman. And so anytime you sign a message, you're going to do these 3 steps right here. This first one is once and for all. So you choose a random element of FP star, and you compute K times G. Okay? No problem. You're just doing, like if you were going to do Diffie-Hellman, it's like you're doing Diffie-Hellman with yourself almost at this point. You have one random multiple of the point, and then you choose a different random K and make another random multiple of that point. Okay? All right, so that's done. Now finally, here's a formula, which we'll talk about for a second, which gives you the signature. And that is the entire algorithm, and I just have to tell you how to verify the signature. Okay, so what's the formula? So the signature will be a pair of numbers modulo p. One of them is, what you do is you just take the x-coordinate of your randomly generated point, your random multiple of g, and you apply this ridiculous map phi to the x-coordinate. Okay, you just do that. So that gives you a number modulo p, because after all, that's what phi does. Okay? And so far, that's kind of just a random thing. But now you do something else. You compute s, which is z plus r times d divided by k. So what are all these things? So k is just a number mod p. That's not 0, so you can divide by it. Let's see. Z is the hash, so that's just a number mod p. R was the number we just computed mod p. Some image of the x-coordinate. And then d was our secret. Okay? So it's completely straightforward to just compute that. For some reason, I was worried about the possibility that s could be 0. And, oh yeah, so if s happens to accidentally be 0, then just redo step 3 with a different random point. R will be different, and then everything else is exactly the same. So you can just keep redoing this. It's very unlikely you'll ever get s equal to 0, but if you do, you just do it again, and you'll get another signature r comma s. It's the same message, but a completely different signature r comma s. They'll look different. Yes, that's it.
I have a question about the hash. Like how hard we would hash the message.
You get to choose whatever hash function you want to use. And I don't really want to go. I should just give you like a 10-minute demo of doing hashes with various hash functions, but I'm not going to do that right now. Just so you can see what this is. I mean, once you just see doing a few hashes, it's a pretty comfortable thing. But I encourage you to Google for SHA-512 and read whatever comes up. Okay, and now we have like 2 minutes. How do you verify a signature? That's the other step, right? And here it is. You have a message, and somebody claims to have signed the message. So you have a Bitcoin transaction, and somebody claims that they made that transaction. They have a private key, which you don't know, but they also have a public key, which you do know. So you look at their signature R, S, and you look at their public key, and you do this calculation on the elliptic curve. The information you have is R, S, and the hash, which is Z, and you also know the public key, so you know G, you know Q, you know the elliptic curve, you know everything. So you just literally you take every single thing you have, all the numbers in the signature, all the numbers in the public key, and the hash, and you just put them together in this little formula, which involves arithmetic on the elliptic curve. Z divided by S, that's division of two integers modulo P, so that really means Z times the multiplicative inverse of S, times G, that means you add the point to itself that many times, and then the same thing, R over S times Q, so you add Q to itself that many times, and then you just add those 2 points together on the curve, and you get a point, and you just check that if you take phi of the x coordinate of that point, you get R, which is the R of the signature. And that's the elliptic curve digital signature algorithm.
That's easy.
It's easy.
Right?
Yeah. So at the beginning, next time I'll tell you how they can possibly screw it up. And I'll also show you, I'll prove that if the signature is correct, then you verify it via this step in the second part.
So we have the question of P plus P, and
Yes.
then there's another one where we have to add the 2 points together and stuff.
Yes.
But the 2014 times
Yes.
P,
Yes.
is there like a function